Hey, my name's John. I work at Connaissance, and I want to say right at the beginning that what I'm going to talk about today, we've been talking about internally in lightning talks and internal conversations for the last few months. I've had a lot of feedback from my colleagues. I'd like to thank them for that. And also, I'd like to say, Connaissance has got a fantastic internal community. We talk about a lot of things. We support each other. We encourage each other. If that's the sort of thing that interests you, and you think that you might be, you like that kind of culture, then you know what to do. Okay, so this is the name of the presentation is Predictably Unpredictable. We'll find out why in a second. So I work at Connaissance. I've been a software developer longer than I'm going to say. But at one point I studied physics at university. I studied physics in philosophy. And I think that's going to come through in the presentation I'm going to do today. It's going to be it's going to start off technical. Then we're going to expand horizons quite a lot. And then at the end we're going to try and use what we've seen to maybe come up with some new ideas and try and somehow take advantage of situations that maybe up until now we think are actually problems. Okay, and I apologize in advance. There's a lot of pop references in here. I couldn't resist. Okay, we're predicting the future. We're always trying to predict the future. We love to predict the future. We love certainty. We're humans, We really don't like to be in situations where we don't know what to do. It happens a lot, We're always trying to imagine the waterfall processes that we used to use. They were trying to nail down everything to the last T, the last dot and the last I. And we found out in time that that's not possible because the world is much more complicated than that. We need to have much better ways of approaching that kind of problem. You probably recognise the picture there from Back to the Future. Biff, we had the almanac, and because he knew the future, he was able to predict the results of some sports events, and then he was able to become rich, and everyone knows what happens when you become rich. But I don't think that's the only way to look at prediction. Maybe we can't predict the future. We know we can't predict the future. So what can we do about that? And with Agile, we try a lot of techniques to try and make things certain. TDD is about making things certain. We don't want any bugs in our code, so we do TDD to make sure that we got full coverage and we're not doing anything that we don't want to do. We do Agile because we want to do iterations because we know that in the future our requirements are going to change. We don't repeat ourselves because we know that, because we don't do things we don't want to do. No, and I've forgotten the acronym. We only do the minimum necessary because we know that in the future our requirements could easily change because we can't predict the future. So I've been watching Tarantino movies recently, so you can see the influence there. I want to start at the beginning. This is the physics influence coming through. I want to start at the bottom. I want to see where is this unpredictableness coming from. Where's the complexity coming from? And I want to start at the bottom and then see what's actually happening. And I think this could be the simplest example of any code that you could come up with, any system that you could come up with. It's one function that calls another. Okay, which function depends on which function? It's quite clear, right? A function depends on the other function. But let's think about it a little bit more. If there's a problem, if there's a bug, where might that problem be? It might be within the function, it might be within another function, or it may be in the outer function, which is passing a wrong parameter, or it's passing something which makes the inside function fail. Right? So there's actually a dependency both ways. The inner function could work, but if it's passed the wrong parameters, then it might fail. So there's a dependency both ways. If we're changing the code and we change the inner function, we could introduce a bug in the inner function, but also if we're changing the outer function, we could introduce a bug in the inner function. There's a two-directional, bidirectional dependency there. And so that they actually both depend on each other. When it comes to detecting bugs, they actually both depend on each other. We can't be sure. What we do is we put a lot of guard conditions inside the functions to make sure that they're called with the right parameters and that kind of thing. But really that's more engineering to try and solve a problem, and we're not going to be able to cover all of those situations. There's always going to be situations when we're introducing a problem, but actually the defect is somewhere else. Okay, this happens in, this happens in all kinds of places. We have the concept of connaissance. You know, we have connaissance is, people heard of connaissance? It's basically it's more connections. Say you've got one piece of code which requires a particular value to be interpreted in a particular way, and you've got another piece of code in another place which requires the same piece of data to be interpreted in the same way. You change one, what happens? Sorry? I hadn't noticed. Should I stop or no? No? Good. Okay. Okay. So the connaissance, the way I see it is, I see it as connections. They're connections between code that's in different places, but it means that you have to change code in one place. Or if you change the code in one place, you have to change it in the other place as well. And sometimes those connections can be completely invisible because you're looking at this file here. You know that there's these values that are interpreted in a particular way. It's sometimes very hard to know if that value is interpreted in other places, in other ways, or whatever. And to be able to make sure that you always interpret those values in the same way, it's a hard problem. And this is another source of a lot of problems. We've got mutable states. So we're changing the code here, we're changing the state. Somewhere else, the code there's more code which depends on the state being in a particular way. We've just broken the code over here. We've changed it here, but we've broken it over here. This is the main reason why everyone hates mutable states. You know, we always try and avoid it. And here there's even worse situations. Some situations which are even harder to detect because you've got a condition in a part of the code. It's a condition, it's not a value. It's a condition which you've added for a particular requirement. And it turns out that same condition is somewhere else. In this case, it's in the same function, but it could be in a different file, it could be in a different module. And you don't know that. It could be a business requirement that have come from different people even, you know, within the organization. Doing a search replace isn't going to necessarily help you because you've got this condition written the other way around or whatever, you know. There's a connection between these two pieces of code which they're very hard to detect, and they're actually very hard to avoid as well. And so this is a quote by Mary Poppendix, quite a very well-known thought leader, commentator. She says the code base grows large, potential interactions grow exponentially because you've got all of these connections happening all over the place. Every new connection has a potential to affect every other connection. So we've got this web of connections within our code and within our systems that actually sometimes we forget how hard it is to detect all of them. And there's a talk about this, and he actually was able to calculate that 95% of his bugs were coming from these kind of situations. They're connections which he was unable to, or which were changed in one place, which then caused a bug in another place. Okay, so this is we're going to move up a level. We're going to go to a more of a system level. And this is a simplified, real situation. Okay, these are the names have been changed to protect the innocent, but imagine we have a service which is, say, doing several things. In this case, I've said payments and stock, but it doesn't really matter. And that's calling behind the scenes some other service. But that other service, when it gets to a certain point, starts to become unreliable. It starts to reject connections. It starts to behave in an unreliable way. And somebody has the great idea to separate our service into two separate services, which is something we do all the time. We want to remove the dependency on the unreliable service. We think this is actually making our service much more reliable because it's now separate from the other system. Okay, so we have these two systems. But it turns out when we separated these two systems, we needed to rely on a shared logging format. Okay, so having to change that logging format every time in both services was becoming a problem. It's a maintenance problem. So everyone does new microservice. You want to share some code, you build a new microservice. So we have a logging service. The logging service is in charge of the format, and if we want to change the format, we just redeploy the logging service, no problem. However, there is a problem, because the service is unreliable. Okay, at a certain level of load, it starts rejecting all the connections. The stock service starts logging all of these errors, stack trace and all, hundreds of lines of stack, overloads the logging service. Logging service then starts to fail, breaks our payment service as well. So even though we've separated the error between, we've isolated the two services, we've got a dependency, and if you notice, we've got a dependency going in the opposite direction to the one that you would expect. So like the code, we've got a dependency which is actually hidden from us. We think the dependency is from logging or from stock to logging service, but actually these connections are both ways in some circumstances, and it's really hard to detect these problems. Of course, I'm sure we all know how to solve these problems. We all know how to the kind of things that we can do. We can add queues or Kafka or circuit breakers and all these kind of things, all these techniques that we've developed to handle these problems. But I'm going to not think about solutions at the moment. Just think about all of these connections which are happening. These really hard to detect connections, which are making our systems unreliable. They just do. It really makes our systems hard to maintain. And what we do is we add a lot of engineering to try and stop those things from happening. But we're not going to be able to solve that problem 100% ever, because these connections are so prominent all the time. So we have this kind of hidden connection between payment service and the unreliable service, which we wouldn't really have expected without really looking deep into the cause of the errors. Okay, so that's the connection side of it. So what happens when these connections start to interact with each other? Okay, these connections are causing problems in one part of the system, which are then propagating to other parts of the system. Okay, so I'm sure none of us would ever do this kind of thing, but it was decided that the payment service had to make a call to the stock to make sure that the payment was okay. What's the problem? Just because the call, and we've got our feature out, and the PO's happy, and everything's fine. And once the load is low, there's no problem whatsoever. But what happens when the load starts to increase? Okay, we get a peak, say, or a time of the day when everyone's coming in and everyone's using the service. So the load on both services is increasing, and it gets to the point where the unreliable service starts to complain because it's getting too much load. Of course, we know the solutions to this. We can give it more resources or whatever, but these are real situations. This is an example of a real situation. Okay, so what happened? Let's trace it through. This is one of the things we'll talk about is how to trace these problems through. So we have a problem with reliable service. The unreliable service makes the stock service stop working. And we saw before that it also makes the payment service stop working because the payment service has this invisible connection. Okay? But when the payment service stops working, then there's no more calls to stock service, so the stock service starts working again. So the stock service starts working, and then after some time, the payment service comes up again, and then everything stops working again. And then the payment service, because it's not sending any load to the stock service stops working again. The stock service gets itself into a loop. It gets itself into what we're seeing, the behavior that we're seeing is that the payment service is starting, stopping, starting, stopping. But the problem isn't there, the problem is with the unreliable service. But the behavior, the pattern that we're seeing is something completely different. And in time and with experience, we get to see what these things are, and we try and put in solutions in place to say it doesn't happen. But then we put a solution here, and then something else happens over here. And then we put a solution here, and then something else happens over here. These are really hard things to detect. And Mary Poppendick again, she's on top of this. She says, it's easy to write bug-free code in isolation. Most bugs are caused the way one piece of correct software interacts with another piece of correct software. This happens. You know, we've got these systems which are correct, they're working, you've tested them, you've done your DDD, you've done your integration testing. You get to a point where they start behaving in weird ways, you know, and there's no way of doing it apart from doing really, really hard performance testing on this to see how they perform in real life, in real situations. And in fact, even performance testing sometimes, if you haven't got exactly the same setup as you've got in production, you can't reproduce the problem. These are hard problems. You know, we've been talking about this week about testing in production and that kind of thing. All that stuff comes from these kind of problems. And then we've seen what happens, how complicated our system got with just 3 services there. This is Netflix service, or one of their zones. Imagine all the connections that are in there. Imagine all the direct connections for a start, and then all the invisible connections, all the hidden connections that we were looking at before. There's going to be things like caching. There's going to be, in fact, you can look up on talks by people in Netflix that are just talking about how their caching has caused massive problems with it because they invalidate their cache, and all of a sudden all the traffic goes to another service, and then everything breaks. Caching, authentication, logging, all of these things are cross-cutting concerns that they really cause problems, and they don't cause problems in that service, they cause problems elsewhere in the service, and it's really hard to find where those services are. We've been talking a lot about postmortems this week, and that's really, really good. There's been a lot of talk about postmortems, and I think that's so important. But I think there's something that we're missing with the postmortems, and that is that these problems can all be solved. We can solve most of them, and we can solve them one by one every time they happen. At 4 o'clock in the morning, when somebody has decided to publish a special offer in whatever service that you provide in the United States, and then somebody has to wake up at 4 o'clock in the morning and try and work out why this service is cycling when actually there's a problem with load in another place. Okay. And this is where the Netflix resilience engineering ideas come from, and I recommend, there's a link here at the bottom, to look at the resilience engineering advocate job description, because they've realized that you can't solve all of these problems. You literally can't solve all of these problems. You've got to take a different approach. You've got to, on one side, you need to continue having engineers looking at the problems, trying to make things as robust as possible, but on the other hand, you need people that understand that this is going to happen, that people make mistakes, that systems do weird things, that you get loaded in unexpected moments, a service goes down, Amazon decides to blow up for whatever reason. You need to be able to deal with those situations because that's the way the world is. The world is unpredictable. Okay, and I want to take a slightly different look now. This talk is going to cover quite a lot of ground in the next few minutes, and really it's about just different ways of thinking about these kind of situations. Okay, rather than just going straight to solutions, like we've been taught since we were 5 years old, problem solution, problem solution. And I think we need to take a step back from that and stop thinking so much about solutions and start thinking more about resilience, making things work even when there's a situation where things go wrong, because they will go wrong. Okay, so this is a way, let's say it's a technique for understanding these situations. Okay, we have the load on the unreliable service. That's fixed, We know what happens when that load goes up too high. It breaks the service. Okay, the load on the unreliable service is caused by the load on the stock service. Okay, the load on the stock service immediately reflects or directly affects the unreliable service. So the load on the stock service goes up, the load on the unreliable service goes up. That's what the S means, that they go in the same direction. So the load goes up on one, the load goes up on the other. Okay, no problem. The load on the payment service goes up. And here is where we start seeing what was happening before. The load on the payment service is causing the load on the stock service to go up. Okay, and that's causing the load on the unreliable service to also go up. There's a sequence of causalities here. And then, this is the key point, the load on the unreliable service has a direct effect on the other two services. We've introduced a loop into the system. And this, if you look at it, it says that it's an O, that's to indicate that it's the opposite direction. So as load goes up on the unreliable service, there gets to be a point when it just stops working. Okay, so that means that the other services stop working, so they can't handle their load either. So we get ourselves into a situation where we're going around in loops. And this is where this cycling behavior comes from. It becomes from this complexity. This is a kind of complexity which is well known. It's called system dynamics. It's quite well studied, and I think there's some tools in there that we can use to try and help us understand these situations. This is a very simple one, but imagine the Netflix situation, trying to understand all of those. Okay? So I want to give you a couple of examples of ways that we can use this. I need to speed up. Ways that we can use this system to look at simple problems, maybe within our organization, okay? So it's another pop reference there. If we're deploying to production, okay? Everyone knows the problems that we can have deploying to production. Okay, this is my pet peeve. So it doesn't matter where you start. This is a loop. It goes round and round, and it doesn't go anywhere very good. Time between releases goes up. You bundle together loads of features. They go into a release. The release then has got all these features in it, which means that there's much more chance of there being a bug because you get all this interaction between the different features. The bugs that you get causes a perceived risk in each release, so people want to release less. So you release less, especially business people. But this has caused us a big problem. This month we've done a release and we got loads of bugs. We need to do it maybe every 2 months. That would be better. But there's a balancing force to this as well, which I think as developers we need to understand to be able to talk about these things. It's a very simple example, but there's a delay delivering features. The delay delivering features means that we need to deliver, so it means that we're not providing value to the customer, so they want to deliver more frequently, and that means that the time to deliver goes down. So what we need to try and do is reduce this loop and increase the power of this loop. And that is a change of perspective, and it's also a way of talking about the problem, which maybe we don't always do. We don't always look at it from all these different angles. And this is just one particular example in a particular project. But there's every organization could have a different set of ideas. Different people have different ideas, and so these loops could be different. Again, another quick example, a quality cycle that we know and love as craftsmen. Doesn't matter where you start, we've got a workload, which as the workload goes up, the delivery pressure goes up. As the delivery pressure goes up, the quality has a tendency to go down, the quality goes down, the bugs go up. It inverts twice. And as the bugs go up, so we have to deal with all the incidents that we get in production, and so we have a larger workload, and around it goes. And so from this is another example of where if you're working in a company and maybe the CEO has seen this situation and the work's going up and the quality's going down, what are they going to do? They go, we're losing money. We're getting less sales because of all these bugs. We're getting a lot of customer complaints, and we're losing sales, falling profit. So what do? Because they're looking at it from a different perspective, the way that we look at it, they think that what they need to do is sell more. They're losing profit. They need to sell more. So they sell more, so they get more requests, which increases the load on the development team, which means the delivery pressure goes up, and we get ourselves into an even bigger loop. And I think these are communication problems. These are human problems. These are the ways that different people see the same situation, and we need to be able to talk about these problems, which are larger than just with our own team, or that we need to be able to look at all the different relationships and causalities which are going on in any organization. And what I was talking about they're called causal loop diagrams. They're one of the main parts of systems thinking. Systems thinking is a way of thinking, if you like. It's a kind of tool that we can use to help us think about these kind of cyclic and difficult to understand problems. System thinking goes further than that. It has the stock and flow diagrams and the archetypes as well, which are well worth looking into. And it has these concepts where I think are quite interesting. The events are the things we see, like this cycling service. The patterns, which are what's going on underneath, what is causing this cycling pattern. The structures is the structure of our system, and then underneath that we have the way we're actually looking at the system. And as you go down the list, the more impact you have. This is a theory. Is a very, very quick introduction to it. It needs more time. There's a very good talk by Jaume Jornet about this that he did in Alevinta a few months ago. I recommend looking at it as a tool for thinking. But it has a problem, and that is that these systems get very big. You have to put a boundary somewhere. And this is an example of a diagram. It's not exactly a causal diagram. This is a diagram by a guy called Mark Lombardi. He was unfortunately he's no longer with us, but he did these diagrams about the relationships, political relationships in the United States, and the way that corruption could spread through a system through the influence of different people. And as you can see, this is a very complicated thing to look at, and there's no boundaries in it. This is going to be hard to sell to anyone. It's a nice, lovely piece of work. He's an artist, this is a piece of art. But the thing I wanted to say about this, or the reason I put this, is this idea of narrative structures. Narrative structures are the things that we need to be able to understand these more complicated systems, these more complex systems, in this language that maybe we're not used to using every day. Okay, so we've got these systems, we've got all this feedback going, and we've seen how these loops cause strange patterns and things that were maybe difficult to understand. Well, it's going to take it to another level. What happens if we get even more feedback? Okay, so everyone knows, I think everyone knows the game of life. They've probably done the kata, and we know how this works. You have a grid of squares, and the life cell is touching less than 2 or more than 3, then it dies, it's dead, blah, blah, blah. Okay, so what that does is sets up a grid, and every cell depends on all the cells around it. And then the next time step, all the cells around it depend on all the cells around them, and all the cells around them, and all the cells around them. So what we've got basically is a network where everything's connected to everything else. And what happens when we get that? There's the code for it. We get these patterns happening. We get these amazingly complex systems, it turns out that this game of life is something which it's Turing complete. You can reproduce any system using this, and in fact they've been able to create game of life using the game of life. I recommend you look at it on YouTube. It's actually quite amazing. And the point is, because we've got all this feedback, and this is the feedback that we're getting in our systems, this is the extreme level, but we've got all of this feedback, we've got all of these causal relationships in our systems. It makes things, so let's say we've got a Turing complete set of defects in our systems, or maybe getting close to it. What people have been able to do is use these ideas, and then they've come up with a lot of other systems which have very simple rules. And what they've been able to do with these simple rules is create processes which actually we see in nature. In nature, we see all these processes. Well, I recommend you look at this site if you're interested in this. Then you can go in and you can play. There's some sort of Java. They don't call them applets anymore. Java apps in there that you can use and play with these things. Actually, quite interesting. And then the next step after that is it turns out that all of this complexity is everywhere. It's everywhere in the world. It's from petri dishes, the typical queues that you're in on the motorway, but then it turns out there's nothing there. It's to do with the complexity. It's to do with the way that your car is interacting with the car in front and the car behind, and that car's interacting with the car in front and the car behind. It creates these waves. It creates these oscillations. We see these oscillations all the time. The waves on the roads. Happens because of the same reason. There's a feedback system, which means that these oscillations come through. The same with turbulence or smoke. It happens in geology, and it even happens up to stars and galaxies. And it also happens within us. It's becoming quite clear now that the way that our brains work isn't the layered system of an artificial neural network. There's a lot of loops going on inside, and what that does is these loops are what gives us the power that our brain has, and maybe even the consciousness that we have. Maybe it's an emergent thing which comes from this complexity which is added by loops within the system. Okay, so we've gone off a little bit into nature there. We've gone off a little bit into things that happen in the world. Just think about that a little bit more. What happens if these individual things that are interacting, what happens if they're intelligent as well? So they're reacting in ways which change over time. And this actually happens in nature as well. We've got all these situations. You've probably seen the murmurations of starlings, which cause these amazing patterns in the sky. It happens here. These are very simple rules, but the actual agents, which are the actual birds, they're reacting in intelligent ways according to the situation that they find themselves. Funguses allow plants to talk to each other. I didn't realize this before, but trees actually talk to each other. They're underground. There's a whole system of interchanges of chemicals which cause trees to change their behavior based on trees that are around them. And this is done via fungus growths underneath, and they also have their loops within them. They're reacting to the context in which they're in. And of course, we all know about insects and ants and bees that create these amazing societies using these kind of feedback loops. They're able to, ants leave pheromones, so that other ants then follow it. The ants follow the pheromones and leave their own pheromones, which strengthens the path. And this is what creates the intelligence that we see in insect colonies. These are called complex adaptive systems. This is every time we're getting more complicated. We started off with systems that just had connections within them and they cause interactions. Then we went to systems which had loops inside them, and that gave us these oscillating behaviors and strange behaviors to understand. Then we went to systems where not only did you have these connected systems in loops, but also each individual system was an intelligent agent. So they're reacting to the context in which we're in. We're kind of like every time we're going up a level of complexity. And this is where I want to start talking about how we can start to use this. Once we know this, how can we start to use this? How can we use it every day in our work and our projects and our relationships, our teams? And one of those things that we can do, actually I'm going to jump over that one. I'm going to go to the bad news first and then the good news. Always do the bad news first. What happens, these complex systems react in such complex ways that it's impossible to determine what's going to happen when you interact with it. If you change this, who knows, if we added more resources to the service we saw earlier on, maybe that doesn't have the effect that we want. Maybe that have an opposite effect to the one that we want. You know, we see this all the time. We give our service more memory. That's happened to me several times. You give it more memory. What happens? There's a memory leak inside. All it does is cause an even bigger crash when it gets to the limit of the memory that you have. This is called the Law of Unintended Consequences, also known as the Cobra effect. Cobra effect is named after something that happened in British colonies in India. They had a problem with being overrun with cobras, and so they asked. They said that they would pay for people to bring cobras in, to catch cobras and bring them in, because they wanted to reduce the number of cobras. So people are quite clever. They're an adaptive system. People are adaptive. They started breeding cobras so that they could take them to get their reward. And then when the governors realized that this was this was happening, they said, "Oh, we can't do this anymore. It doesn't make any sense for people to be breeding cobras when we're trying to get rid of them." And so what happened was they said, "Well, we're not going to give you any money for the cobras anymore." They stopped the plan. And what happened? All the people that had these cobras just released them into the wild, and there was more cobras at the end than there were at the beginning. This is why they call this the Cobra effect, because it's such a clear example. But rather than use the Cobra example here, this is something that came up this week. They're trying to reduce the number of mosquito, or they're trying to reduce the malaria which is spread by mosquitoes. And so their plan was to introduce mosquitoes which have been modified genetically to be sterile. Okay, and what's happening is happening now. If you look at the date on that, this is this month. Turns out that the modified genes that they've added to the population of mosquitoes have actually got into the population of mosquitoes, the native population of mosquitoes, which means that now those mosquitoes are resilient to the very thing that they're trying to do. So it's had the opposite effect of what they wanted. They've introduced genes into the natural population. So now the very thing they wanted to do by introducing the sterile genes, it doesn't actually work because they've already got these genes. And then we'll go back to, this is the good news. So that's one side of the coin. One side of the coin is the unexpected consequences. The other side is exaptation. Exaptation is when you have something that's supposed to do one particular task, but because it's so complicated, it turns out that it's actually better at something else. This happens a lot in nature, happens a lot in tech as well. I'll give you some examples. This is an example I like. This came up recently. Spiders can fly. Did you know? And the way they do that, it wasn't known how they did it. It turns out what they do is they spit out a piece of web. They go to the tip of a tree, the tip of a branch. They eject some web. The tree is negatively charged. The web that they eject is negatively charged, so they repulse and it gets projected out into the air. And then because of this magnetic field on the web, they're able to fly over the magnetic fields, the Earth's magnetic fields, and they're found, hundreds of kilometers of altitude. But this is an example of exaptation because the web, the silk that they produce is to make webs. But because of this negative charge that it has, they've been able to use it to do something completely different. Completely different. But it's there. It's an example of exaptation. Maybe even the web itself was an exaptation of something else. Maybe the web was because they used the silk to travel or something, I don't know. But this is an example of something which has got this complexity, which then you're able to take advantage of that to do something completely different. And actually, there's a lot of companies that do this. A lot of, the famous example is that Slack wasn't supposed to be, a product. It was supposed to be an internal tool of the company that the guy was setting up, but it turned out to be so popular that they decided to release it as the product, and that became Slack. And I've got an example of my own. I've got my own company, so a background project that we started doing information for local towns around the Catalonia area, and which was nice. We had a lot of information about the towns, and then one of our clients said, how about we do a loyalty system for people in the town, so that if people from the town are buying from the local shops in the main street, we can try and attract people to our local economy. Turns out that is much more appealing than the other system that we had originally, which was just information about the town. And now our company is basically a company which is about loyalty systems, and we sell that to different customers. Completely changed. Okay, so we were talking about adaptive agents. Now let's talk about even more adaptive agents, humans with their own intelligence, with their own ways of behaving. People have been able to simulate or been able to understand the way some humans or human communities, some humans behave, or say that, for example, they've been able to model how the Ebola virus in Africa. They were able to see where the major paths of contagion may have gone because of the way people move and the way people behave. They were able to reduce the risk from 14 million possible infected people to, I think, 150,000. And they did that by looking at the way people behave, the way people move, the way kind of travel that they do. Okay, and actually this week it came out that some people are trying to now model entire cities. They're modeling how people get to work, what type of jobs they have, when they get married, when they get divorced, when they have children, the school route. They're actually modeling all these things with some success. Some success. There's a thing going around Twitter at the moment about, when you finish your PhD, they take you into a room and they tell you something. This one came up the other day, which is perfect, because actually when you're modeling complex systems, they take you to a special room and tell you that people are not actually particles. True, it's true. And there's a lot of examples of this. There's a really, really famous example. This is an example of in Mecca. I think there's I can't remember how many millions, but it's an enormous amount of people go to this place. They move around, but simulations were done. They were able to detect in certain ways certain areas which were becoming congested and causing problems, in the same way they did with the Ebola. But it wasn't enough, because one of the people that was involved, he said the little dots on the screen are just one method of testing a set of assumptions. If the weather changes, or there's a sudden noise, or a bad smell, you can't really reduce an individual's mindset to an algorithm. I think that's totally true, and we see this every day. There's a very, very common situation that we see this in. Somebody says, you have to do this so many times. Okay, and then so what people do is they game the system, and they try and turn a measure into a target, which is not necessarily what you want. A way we try to reduce this kind of complexity in human systems is by reducing or increasing the constraints on the system. That is, reducing the number of connections, and hierarchies literally reduce the number of connections that people have with each other. But as Kevin Henley said, and he talked half an hour about this, these are not the way the organizations work. Organizations are not trees, they're not hierarchies, people are not hierarchies. And we see this in Agile as well, and actually Agile in this way is actually in trying to use complexity to get the best performance from a team, because a team which has got all of these connections inside it, I'm sure probably all of us now work in teams where we're multidisciplinary teams and we talk to everyone every day. Small teams, but we talk to everyone every day because that gives us maximum ability to adapt. The real organizations aren't like that. Real organizations are connected like this. You walk past the the coffee machine, and you talk to the CTO, and then the CTO goes and talks to somebody else, and then you talk to somebody. This is the way companies work. It's the way people work. Okay, and this is the advantage of these kind of systems is self-organization, because these teams have so much complexity within them, because of the connections between the systems. It means that they can self-organize. And I don't think we use this enough. Self-organization is such a powerful thing. For example, I worked in a company once where we were selling a product to people in Japan. It was a sort of data management system and for producing circuit boards. And they were selling it, and the CTO would go to Japan and try and sell it. And he said everyone what they actually wanted was to be able to import their own data. They had their data as CSVs or whatever. They had all their data in their own format. And he said if I could just have one green button that imported whatever data from whatever system into our system, I could sell a lot more. And he said, and he was a very, very clever guy. He said, I know this is impossible. I know it's impossible. I want a big green button. I know it's impossible, but I want a great big green button. So what happened was the people in the team, it wasn't their first thing on their mind. They had to get their job done, every day. But they had this thing in their mind. We want this big green button. We want this big green. And so over a few days or a few weeks, people started coming up with ideas. People started moving in that direction and people were importing all kinds of formats because they'd already been thinking about this. How would we import this? How would we import that? Detecting formats automatically. It was a form of self-organization because he was just giving this impossible dream of something which could happen, and the people themselves were organizing to make it happen. Okay, so come back to Netflix again. We've got Netflix as a social technical system. It's actually a complex system of people with complex systems of technology inside them. We've got complexity, all these different levels. We've gone from complexity from a connection level through complexity through feedback, complexity through intelligent agents, complexity through human agents, and now we're putting it all together and we're creating these social technical systems with technical systems and social component as well. And if you get that, then I'll take points away. So this is the last part. I will go really fast. How can we navigate this kind of uncertainty? We know that things are uncertain. I know we try and remove the uncertainty. We try and make it not happen, if you like. But certain things that we do help us navigate this. For example, the short iterations in Agile are literally because of this. We know that the requirement's going to change next week. We know that our team can change next week. We know that the context can change at any time, so we do short iterations to make sure that we can predict as much as this short time period with more certainty, as much certainty as possible. But there are other ways, and this is the final part of the presentation, which is about some maybe harebrained ways that maybe we could start thinking about and start incorporating it into the way we work, which goes beyond what we do with normal Scrum or Kanban or whatever, but actually enable us to do things which take advantage of the complexity that we have at our disposal. We shouldn't see it. I don't think we should always see it as a negative thing, but as a positive thing. One of these ones is that, I don't know if people have heard of the ODA loop. John Boyd was a fighter pilot in the American Navy, I think. He was one of the best in the world. And the way I understand it, he didn't really understand why he was the best in the world. He was able to fly the plane in ways, and he was able to beat people in simulations, in simulated dogfights. He was able to beat them every single time, and he didn't really know why. And so he went away and he thought about it, and he said, how am I able to do this? Because it's a context which is changing all the time. It's the most complex situation you could probably have. 2 airplanes doing all kinds of things, and you having to react in real time. And he came up with this system which was observe, orient, decide, and act, and repeating this. And if you look, it's feedback all the time. And feedback through the environment, which goes back into the system. And there's a lot more to this. This is just a diagram of like the main components, but there's a lot of philosophy behind this about how he goes about it. And people are using this. People are starting to think in this way. rather than thinking about simple iterations with fixed outcomes, start thinking about real-time adaptation to what's going on and coming up with ways to adapt even more quickly than we do at the moment. And I think that it's very telling here that there's so many connections going to observe. We need to know what's happening. We need to observe the situation to be able to orient ourselves to where we want to be in that context and make do the actions that we want to do. Okay, and so observation is so important to this, and this is why we need metrics, and it's why we need to actually look at what we're doing. Another system, I don't know if you heard of some Wardley, I heard him mentioned earlier. He's got this idea, which is about the pioneer settler town planner. He set up his business in a way that it had projects had three different types. They were projects which were new, which were innovative. They were people coming up with ideas all the time. And then when one of these ideas actually became useful, they would send it to another group of people, which were the settlers. They were the ones who were able to actually build it, to make it strong, to make it robust. And then they sent it to another group of people, which were the town planners, which were people that just like to be given systems and then to maintain them. They just want to make sure that it works really well, it's robust, resilient. This is another way of using complexity, because we can use the way that people work especially in the pioneer area, to just do a lot of experiments, experiments all the time. This is where novelty comes from. It's so important to have a safe to fail environment. If you can experiment and fail in a safe way, then you can produce novelty. And then once that's working, you use other engineering techniques to get to the point. Very, very similar. Kent Beck, I've added this here because we all know Kent Beck. He's got this 3X system, which is basically the same thing. Well, very, very similar. This is more oriented to software design, software development. But again, this has come from Facebook. Facebook would have teams doing a lot of experiments, a lot of things which were happening, a lot of ideas that they wanted to explore. When one of these ideas actually made sense, when one of these ideas actually started making some money, then they would go into an expand phase, and they'd try and make it into a bigger thing as they could. And it's a different mindset. You have to apply different kind of principles, different design principles to the expand phase. And then once you've got to a point where there's nothing really you can expand anymore, it's just doing what it has to do, then you get to the extract phase, and then you try and get as much out of it as possible, you maintain it. And then my personal favorite, I think is going to be big in the next few years. This is a system by Dave Snowden. This is a framework. This is a framework which comes with a lot of methodologies. It comes with a lot of ideas. It comes with a lot of the ideas that I talked about earlier about using complexity for what it is. And if you look at the 4 different areas, we've got a movement between what's simple, things that don't have interactions, self-interactions, things that are easy to understand. These are things that we do every day. I don't know, some kind of example like a CRUD system that you just generate and it's done. No, we can do that. You can write a document and tell somebody how to do that, and you don't need to do any design. You don't need to think about it at all. Complicated system, maybe this is the things that we know how to do, but you need to think about it a little bit. You need to know, you can work through it, but you need to do some analysis. So the sense, analyze, respond, you can actually look at it, you can apply good practice to it, because with experience you can look at the things, what needs to be done, you can actually go through it, you can analyze it. This is actually where some upfront design, it makes sense, because if you know that you need a system and you know fairly well what it needs to be and what it needs to do, then you can avoid rework by putting in place the minimum, but the things that you know that you're going to need. And then we get over to the complex area. This is the things that we were looking about earlier. This is where everything connects with everything else, but this isn't a problem. This is where we sense and respond. We actually we probe the system, we experiment. We're okay if it fails, because this is a complex area. We don't know what's going to happen. We can't predict what's going to happen. So we probe, we find out what happens, and then once we get ideas, we can use that. And interestingly, Dave Snowden puts agile techniques on the border of these two. So we're using agile techniques in situations where we're a little bit complicated, we're a little bit complex, when we're trying to drag them over in 1 week sprints or 2 week sprints into the complicated area where we can actually handle it and we know more or less what we need to do. So Agile in his framework is the border between complex and complicated. But there's so many other techniques that he applies to this. He uses a lot of the ideas we saw earlier about the unintended consequences and that kind of thing to actually take full advantage of the complex area. And the chaotic area as well, that's where things just, things are just totally out of control. But that's also got its uses as techniques that we can use and we can exploit in that area as well. This catastrophic fold at the bottom, this is where you pile a pile of blocks, children's blocks up in there, and then it gets to a point, really simple, you're just putting one on top of the other, it gets to a point where the whole thing just collapses. And that's something else that we need to bear in mind. This can be really fast transitions between chaotic and simple or obvious. And I just wanted to give one simple recipe. I'll try not to do recipes in this talk, but there's just one simple one which shows how that worked. They have this idea, or one of the methods in the Knevin framework is the anecdote circles, because people have this tendency to put their own perspective on things. So we can use that. We can say, let's gather anecdotes. Let's just what made people happy, what made people sad, and what did somebody remember? What's something which really stood out? What made them laugh? They're really things that people can relate to, and we can really supply information really fast, and it's not subject to these cognitive biases. We can synthesize that information, and then we can look at the impacts and any decisions that we need to make. Okay, so this is final section. We've seen complexity as complicated. Complexity is complicated. This is the sort of thing where we can do upfront design, and we can actually take advantage of the what we know, but not to the point where it's unpredictable. It's still predictable, so we can actually do some analysis of what's going to happen. Unanticipated is when things happen that we just hadn't anticipated. We saw a lot of examples of this in the talk. Unpredictable. This is the complex area. This is where we really don't know what's going to happen. Let's do some experiments. So let's set up some safe to fail areas that we can take advantage of the unpredictableness of this, because that's where we're going to be able to do create novelty, because we don't know what's going to happen, so we can use that. And this is the key point to take away, is the complexity is opportunity, because this complexity gives us the possibility to innovate, to add resilience to our systems, and I think it's going to be let's say the future of agility is going to be taking advantage of these situations, taking advantage of the complexity that we have, rather than trying to reduce it, to actually increase it, and let's get full value from complexity. And I encourage you to look at these. I've just gone through these things really fast. Encourage you to look at the different areas. These are things that go beyond Scrum and Kanban and things like these. These enable us to maybe do things that we're not doing at the moment. Uncertainty is an uncomfortable position. Certainty is an absurd one. There's a famous quote. Let's embrace the uncertainty. Let's embrace the uncertainty and get as much out of it as we can. Okay, that's the end. My Twitter there, if anyone wants to talk about this anymore. So I tend to tweet about science and software. This is kind of area that I like to talk about, complexity and that kind of thing. Okay, is that it?
Yeah, so some question. I think two, because we have the long line.
Hello. Okay. For me, thanks for the talk. It was really interesting. I will need to think about a lot of stuff. I was just thinking about what you said to have three types of projects, or three parts of the project: the innovative part, the kind of maintenance part, and then the kind of just end part. I don't know the exact word you used. But so do you think nowadays organizations are well built for that, because from my experience what happens is that the very exact same people do the exact same 3 parts of the process, right?
I don't know of any.
What would you change if you could put like the perfect organization?
I would like, most of the companies I know of don't have safe to fail environments. They just don't. They want whatever they've designed, they want it to work. And you need to change that mindset. You need to have whatever you designed, you want it to work if it should work, and not work if it shouldn't. This is how the scientific method works. You try things, and if it doesn't work, you put it to one side and you try something else, or you adapt it and you try something else. We don't do that. We don't do that in software. We don't like throwing things away. We really don't like throwing things away. I think we should. And actually, if you think about it, we love programming. We really shouldn't mind throwing stuff away, because it means we can do it again. But I find a lot of people don't like. In fact, somebody told me this week, oh, I had to change this. Oh, I spent so much time on it. Embrace it. You know, this is a chance for you to do it, and do it again, and do it better, and do more. I like to have that kind of mindset of, let's throw it away and try something else. Let's throw it away and do it better. Let's throw it away and maybe create something new. You know, and these are things that we can apply. I think we could take this away and apply it straight away, but at the moment we don't. This is really the reason I wanted to do the talk, to encourage people to try it. You know, I'm trying it in my projects and getting some good results. And I really think it will be the future. In the future, it'll be the way that more and more teams are working.
Okay, this is the last one. After you can ask what we can talk with them.
On your last slide, you used the word complexity repeatedly, which confused me a bit, because
Yes.
I need to know your definition of complexity, particularly as it was preceded by Connaissance Framework, where he makes a distinction between complexity, complex and complicated, and you said at the start complexity as complicated. So
Yes.
what's your definition of complexity?
No, in fact,
there?
was one thing I tried to do through was to show the levels of complexity. The complexity is changing all the time, and everyone's using different definitions all the time. People are using, and in fact, this is what this slide means, because we use these words all the time. We use complexity when something's really complicated. Someone's just given me this document, it's really complex. No, this document isn't complex, it's complicated. Someone's tried to express something and they've done it in a way which is hard to understand. But if you spent enough time looking at it, you can understand it. But people use the word complexity. This is complexity as complicated. And then we use complexity because, oh, this happened, oh, this is weird, I have no idea why this happened. Or complexity in its mathematical sense is unpredictability. This is when we've got so many connections between the things that we literally can't predict what's going to happen. And complexity opportunity, that's the sort of the tagline of the talk. So it's one key point. It's a good question. We use complexity in different ways, and that's what I've tried to resume that in this slide. Maybe I didn't do it very well.